All right, thanks for the opportunity. My talk is entitled Benchmarking Stokes Flow. This is kind of what I like to do. I'm going to walk you through the last, 4 or 5 months. So effectively, in terms of motivation, obviously we have the code as it is now, and we have by now markers and compositional fields. We have this continuous Galerkin, we have the volume of fluid method in there. We have a true free surface by means of the ALE formulation, or we can use a sticky air. As many of you know, there is always the question about the averaging, the marker projection. This is work in progress, I understand. I put here on the right, do you see my mouse?
Yes, we can.
Cool. Okay, so on the right here, you see the a few papers, relevant papers pertaining to basically transport. And so if you want to check our codes, or in this case, aspect, we can use manufactured solutions, which is great for verification, but it's often isoviscous and instantaneous, not necessarily close to geophysical problems. When it comes to the free surface, we have no benchmark except for this relaxation of sinusoidal perturbation that I know of. And then when it comes to large deformation flow, I will argue that we don't have a real benchmark, even for linear isoviscous cases. I might come back to that later. Second motivation is I teach computational geodynamics at my university, and so I have students writing their own codes, and therefore they need to check it and benchmark it. I work with researchers who write their own codes, like this paper in 2020. I work with researchers who adapt and or test existing codes, like this paper we did in JGI this year, GGI. And I write my own educational codes in my field zone projects. All in all, I need to and like benchmarking and doing it right, whatever that may even mean. But when it comes to free surface and or large deformation, all I got is effectively here glorified Rayleigh-Taylor instability problems, with on the left the almighty and all famous von Keken, it's all 1997 problem. All kinds of Rayleigh-Taylor instabilities, and on the right we have the sort of, I took an example of manufactured solution. All of these are in aspect, by the way, so you can find them in the manual. But I will argue that we need more benchmarks, because we always do, especially when it comes to large deformation, and this is what I want to talk about today. I could start very easily by saying, okay, well, let's take a 2D problem. We have a square sinker in a model in the middle. There is no analytical solution for this. We have the material interface that is aligned with the mesh. It's instantaneous, simple boundary conditions. Think free slip, no slip, that sort of thing. Material model I can write just to do this. It's 2D, so it's cheap. I can use very, very high resolution. By means of extrapolation, I could actually arrive at, quote unquote, the velocity field on high resolution grids. But let's face it, it's a bit too simple and nothing moves. So moving on. Obviously, I can make it round and it gets a bit more interesting because under the same circumstances, what I have now is I have an object which does not align with the mesh. And then we need to introduce this question of averaging and projection and the use of AMR. So it's interesting in its own right, and we've been doing that, and it's in the papers. But it's still instantaneous, and it doesn't really get us any further in terms of large deformation. Yet, what we can do, and I have done, is actually you can write a code which is based on triangular elements. I'm making sure by means of this triangle software, I build a mesh based on a constrained Delaunay triangulation. And I'm using the Cruzeiro-VR elements, which are second order in velocity and discontinuous linear pressures. And so this is the mesh here on the left. And what happens is that when I solve the problem, then I make a cross section vertically from A to B. Here you have the velocity. Then what happens is that I quickly notice that no matter what kind of parameters I use in terms of element size or number of points to discretize the sphere, I get what I would call the single solution, right? There is no oscillation, there is no weird behavior. Everything falls under the same pixel, which is not exactly a good measure, but it reassures me that effectively what I'm looking at is probably the solution down to some epsilon error. Here you have the velocity, here you have the pressure. What is gray is inside the sphere. So that is fine, but it's a bit limited. Yet, what we can do is actually use, for instance, so this is an excerpt of my document, compendium document, Fieldstone, where you have here effectively the results of the code I've just shown to you. And very, very quickly in terms of resolution, so increasing resolution to the left, we have a stable solution in terms of the VRMS. And then if you look at the purple lines here in bold, you'll have aspect results. And then of course, now we can start talking about which of the averagings yields the best result for the VRMS, assuming that my finite element code, of course, is the right solution. But what I see is that by increasing the resolution with aspect, I get closer and closer to the triangle-based code. So that's fine. But then, of course, it's still not large deformation. So it might teach us something, but let's face it, it's not exactly groundbreaking. So then I thought, hey, how hard could it be? I'm going to add sticky air on top of that, move the ball right below the surface, so the interface between the sticky air and the mantle, and then I can actually let it run over time, right? And without remeshing, so effectively the top row is the initial time, and the bottom row is actually when I stop the simulation, because you see the triangles get highly distorted, and then the accuracy goes away. So that was just a tryout basically, and that was some time down in October or so. And I felt, okay, well, that's interesting. I can do that at pretty much low cost. I just need to advec the mesh, and that's about it. But the great thing is that when I looked at all kinds of simulations, so A would be the area of triangles, and N is the number of points I use to discretize the surface and or the ball, I see that pretty much as soon as I have a decent resolution, everything falls under one line. So I have the sphere center position as a function of time here. That is pretty much one line. Then I have the maximum velocity in the domain. I have the VRMS. I have the minimum of the topography. Everything looks nice because I don't have any elements with multiple materials. It's all either your air or your fluid or your ball, which of course led me to run aspect models on this. And this is work in progress because there is a lot of things to test in aspect, as you may know. I've explored here, for instance, the use of AMR, so GR and AMR. And what you see here is that for arithmetic averaging, by increasing resolution, aspect gets closer and closer to what I would hope to call the right solution. And this is the VRMS, and it comes from underneath, if you want. By using the harmonic averaging, then we start actually too high, but then by using more and more resolution, we get aspect to converge to, once again, what I hope to be the right solution. And of course, there is geometric averaging and all kinds of things. And of course, you have markers. And so this is, there is a lot of input files here to be written and run in batches to make sense of the whole thing. But this is an interesting exercise nonetheless. But then it led me to think about the mother of all benchmarks, which we've been discussing for so many years that it's time to put an end to this. So yes, this is the Van Keken 1997 benchmark, the Rayleigh-Taylor benchmark between codes. Just for information, it's been cited 236 times. So it is a relevant paper even 20 plus years later. And for those of you who are not acquainted with this benchmark, on the left here, you have the setup. It's a Rayleigh-Taylor experiment, obviously, where you have a lighter fluid under a heavier one, where you have a delta rho over rho of 1%. The viscosity ratio could be a factor 100 or 1. And in this case, I'm focusing on 1. And what I have here is effectively what people report usually. And people report, what I call the fluid spatial distribution. So effectively how the system evolves over time. And this is the yellow and purple evolution thing. So for those of you who are friends with me on Facebook, you know where this came from, what I posted last week. And what people post mostly is the evolution of the VRMS as a function of time. And the first peak here corresponds to actually the first provoked, it's called, triggered upwelling that is triggered by the deformation of the interface here that we put in there. And the second peak corresponds actually to the second upwelling here. And that's pretty much all there is to it. Usually you will see, case in point, some of the literature, not all, but some, you will see that people report happily what it looks like at the end, and or the shape here. So basically you have the first peak, second peak. Here have aspects from the manual, etc., right? So if you want to know more, the all the list I found is actually in there. So effectively, if we look at the study itself, 1997, this is straight from the study. They had different codes, and okay, it was the 90s, so they didn't have the opportunity to run it at super high resolutions, as you can tell from the left column here. Basically, here we have the time of when the VRMS is maximum for the first peak, and its maximum. So effectively, people report the top here, or the top value, the middle here. But the second peak, as a lot of you may know, it's actually a different story, right? And I'm showing here the worst case scenario, which is actually in the aspect manual, where you have the second peak, which is all over the place. And the aspect best case scenario, which was put recently in, and that's the VOF method. And you see that here, the second peak is actually well behaved, and increasing resolution seems to yield a second peak that is, which location and height is resolution independent. So I would be happy and tempted to think that this is the solution, but this is the first time I see such a nice behavior. So what I've done is I've written my own code based on what I've shown you before, basically, except that this time I have actually here on the surface, I've used something called a marker chain, which is literally what it is. It's a marker, and you chain them together, and you make sure that they represent the interface. I have the remeshing every time step through this triangle program. I've used the mini and the Crozier Raviar elements, and for now I'm focusing on isofiscus. And my parameters are initial number of nodes on the marker chain, the refinement strategy, because you can tell the chain is going to lengthen over time. So obviously I should add points at some point. The average size of the elements here. So yeah, basically your resolution if you want. And of course the CFL number. And lo and behold, I was very happy to see that when I run the code, once again, no matter what kind of strategy I use for the CFL, for the refinement of the surface, the number of elements, whatever, basically I get a unique VRMS. Here you see the evolution of that point over time. So that's the Y coordinate of that star over time. All the models actually align on one line. And rather interestingly, here I'm measuring the length of the interface. So I'm integrating every segment, I measure the length, and I add it all over time. And you see once again that my interface length, it's the same for all models. So I'm pretty happy because I'm thinking, okay, well, then I have a resolution independent, CFL number independent result, right? And then when I put it in the context of what I could find in literature, then the black lines are the von Kaken paper, and they are pretty much all over the place. We have here all my FEM codes in different colors. We have here this paper we did this year, which used 2 codes with the VOF method. And here I have aspect, best case scenario with compositional fields, and here aspect VOF, right? And it's a bit of a mess. So then I isolate peak 1, only my code and aspect, and peak 2, my code and aspect. And what you see is that effectively my code is purple. So here we have a nice agreement, and it aligns very, very well with the VOF method results, and a bit less with the compositional field, the smooth compositional field approach. But rather importantly, for the second peak, I've got the same thing. So effectively, my results agree very, very well with the VOF results. And the smooth compositional field approach is a bit off. So that is pretty much my conclusion in the sense that this is me 8 years ago at AGU presenting for the first time something with and about aspect. And my first presentation was about the von Kaken benchmark. And yeah, it's kind of a full circle thing in the sense that this is obviously what I've shown you is a work in progress. I still need to run aspect with all kinds of batch scripts. My codes are on GitHub, so you can grab them and play with them and convince yourself. Obviously, I found that the Crusader VR element is much better than Mini, and soon I'll be running P2P1, like the Thieulot version of it. I would dare to say now that Van Keken et al. 1997 is a benchmark. At least I hope to have convinced you that it is a possibility. And as soon as I understand how the 3D measure works, we could repeat all kinds of exercise like this in 3D. So if you want to benchmark your free surface or large deformation of some kind, I'm actually pretty willing and interested, because I think we have an interesting sort of methodology here. So that's it for me. Thanks.
Thank you. So we're about on time, so there's not much time for questions now, but we can have that in the discussion later. Sure. Just quickly, when you say that the Van Keken benchmark is now a benchmark, you mean because we now for the first time have two codes that actually more or less agree on the solution for the second peak?
Yeah, of course I should run it to insane resolutions and maybe do some extrapolation and do some more careful analysis, but I find it reasonably convincing. Okay. And these are radically different methods, but both of them guarantee, at least that's what I understand of the mass conservation, volume, all kinds of nice properties. And of course mine as well, because I, of course, track mass conservation. I didn't show it. Yeah. So this is why I'm kind of optimistic, but I could be wrong, obviously, but optimistic.
Okay, thank you.